last time we got up through, we were working on finishing up the inertia formula. So I thought I'd review just a tiny bit as to where we were. I think we had some odd robotic arm kind of thing. The key thing that we were working on, though, was we were working on, oh, I don't want to put it that way. We're working on, there we go, rotary motion as opposed to linear motion, because once you get to linear, we've got to deal with whatever translation device you're using. And so we'll go through that in a little bit. But right now, that arm we had was, let's see, I think we had a little mass, and then we had some sort of arm, if I remember right, a couple gears, just making stuff up, you know, some sort of ratio, and then a shaft, coupler, and then finally motor, right? So we had some sort of rotary motion, all look about right. And we'd finished up the torque formula, and rather than rewrite that here, I think we had kind of gotten to the point where everything was lining up and didn't have any more inefficiencies or any more gear ratios. And so if it's directly connected to the motor, it's a direct inertia that you have to turn. And we didn't really go about solving for instance, the coupler you would probably go look up, but if you couldn't look it up, just keep in mind that this whole exercise is an estimation in the first place. You're doing the first motor sizing when you don't have anything built. It's all in SolidWorks, it's all in sketches. You're trying to get ideas as to how much things are going to move. So it's not that important, except for to know maybe you needed to do the, if you're doing the coupler, maybe you needed to do, you know, treat it as a solid cylinder. And then you could go look up the formula for a solid cylinder. This one is so common that what is it? It's usually the inertia is pi. The one I use the most is pi times the length, L times the density times R to the fourth, and I think that's over 2. Something like that. It's in the motor sizing handbook. It's pretty common. And if you had a hollow cylinder, you could subtract one from the other. And the key place that people make errors in this is right there. Actually, sorry, not that. That's not where they make it. Right there. That's the error spot. Because when you put in diameter instead of radius, it becomes a real problem since it's to the 4th power. So speaking of that, let's go through some common errors in motor sizing. I'm just going to cover this off right now because that's one of them. But there's really kind of 4 main mistakes that people make. First is they don't include all the terms. So it's really easy to guess that something is not going to have a torque requirement and to leave it out. But in general, one of the things that you're going to want to do is do this work for review. You need to do the work not for yourself, but so somebody else in your own group can review it. Your boss could review it. You don't do work anymore. This is why you comment code. When doing this work, if you know that you don't have a gravitational term, if I'm writing out the formula, I'm probably going to say, you know, T acceleration is torque due, or torque peak is torque due to acceleration plus or minus torque due to friction plus or minus torque due to gravity. I'm probably, if I'm going to make that 0, I'm probably going to put down an asterisk, you know, as to why it's 0, just on the paper. And it's mainly not for you, it's mainly for a reviewer, because you got to have this stuff reviewed, it's really easy to make mistakes in this whole operation. So do include all the terms, and I guess I'll just finish off that last one, plus torque due to any work. So that's a gravity. There we go. Another thing that people don't do is they don't, common errors, yeah, don't carry units. So this is, motor sizing is probably more unit intensive than anything else you do. It's a whole bunch of different torque and frictions and coefficients, and your customer, when you first go and get information from him on the load that's turning, or you know what they want, they tend to think in pounds and ounces and inches. Sometimes they won't, and they'll immediately do the conversion. But when I wrote up the 7 steps of sizing, I wanted to have it fast, and I wanted to not make mistakes. And so I really made it so that I don't really care which set of units you're using. And there's only a couple little catches to make sure that you're using proper units of inertia, for instance. But the thing that I found is, if kind of my rule of thumb when I'm plugging in numbers, once you've got past the formulas and you're confident your formulas are right, is anytime you write down a number, you should write down the units, and just don't get sloppy with that. And then every time, watch those units cancel, look at the end, and make sure you don't just put Newton meters at the end unless you actually watched all the terms cancel out, and finally it's like, yeah, that's a Newton meter, not a Newton inch, or you know, something. And so when I look for mistakes, or when you look for mistakes, that's a really easy place to find them, is actually do your unit, go back and look at your units. Another one is the vectors don't match the sketch. Particularly, what happens here is mainly in the direction that the forces or the torque are operating. It's just, you got to really pay attention. If you draw something, make sure that it's not normal to that, it is in the right direction, creating that force or torque that you're after. And then finally, the fourth one is using diameter, not radius. Those are kind of your 4 things you got to look out for, that I can think of off the top of my head anyway, that you can make mistakes on. So we are almost done with TA. There's one more thing that I need to mention on it. So let's finish that up. So kind of, let me stop that. So let's go back and say we had TA was, and it started, and you had inertia of mass. Oops, somehow mass. And then, if you remember, everything went in the denominator, and the 2 things you're looking for in this term, when you're dealing with I alpha, yeah, I'll get back to that, is you're looking for inefficiencies of gearing and gear ratios, and those were squared plus ... And then finally at the end, we probably had inertia of the coupler plus inertia of the motor. Don't forget, we got to turn the motor. And we don't really know right now which one of these is the dominant term of the 7 terms that are in here. You don't really find it. You could guess, And if you did a lot of these, which you guys, that's one of the problems, you guys aren't likely to do a lot of these, so you don't get lots of practice or gut feel for this stuff. So you just got to plug in the numbers. Term out here is alpha, I alpha. Typically, you don't need to get to alpha. You can use, you do need to make sure that that you are omega max. And so omega max is the maximum speed you're reaching during your acceleration. And then TA is the time that you're accelerating. And that's essentially that little triangle, right? That was in the motion profile, that was accelerating up, where this was T sub A. I'm running out of room. This is omega max. So really alpha is the slope of that, right? And you'll notice that I put in a 2 pi. Anybody know what the units of 2 pi are? Of 2 pi r? No, not just the units of 2 pi, not 2 pi r. It's kind of important.
Radians.
It's not unitless. That's the goofy thing. Part of it's unitless, but it's actually used as a conversion for this, right? What'd you say? I think what you said.
It's the radians.
It's radians per something, though. It's really important. So let's go to the next page.
Oh,
here.
radians per revolution.
Right. So omega out here at the end, omega is, or I'm sorry, the 2 pi. When you write that down and you use your units, it's radians per rev. And that's needed because over here, you're going to have, you're going to need that revolutions to cancel at some point. And so you need to get that into radians per second to get the proper torque out of this, right? The one other thing that happens is if you're using English units, you're going to get, I'm going to go to the next page here. So that was page 1. So let's go to the page 2. So the thing that happens is you end up with a torque, and if you've been using English units, you're going to end up with an inertia, and probably it's in ounce inches squared. That's the units that you're going to get when you do m/r squared. If you're using not true math, forget about trying to get to slugs and all that kind of stuff. It's okay to use ounce inches squared, or just keep in mind that to get from ounce inches squared, you've got to get rid of per second squared. You've got to get rid of G. You need to divide by G. And once you divide by G, then you're going to get ounce, inch, seconds squared. And that's the proper unit of inertia, because ounces, just I mean, when you first start doing this, you get all hung up on, is that slugs, pound force, what is it? Just remember, ounces and pounds have gravity in them. And you can't use them as a force that way. You got to take out the gravity, or you're off. So typically when you have the T sub A, and you have this term with the inertias, ... and over here you had alpha. If you're using English units, you got to put that in there. And then that takes care of your, and gets you back to the proper units of inertia. If you're using regular newtons and centimeters or meters, or then you're fine. You don't need to worry. You won't have that 1G term. So, okay. Keep in mind now we've done the peak, or you could also call this, if you wanted, you could call this worst case. We had torque to accelerate, and we've done that one. We're done with that. It's the hard one. The rest of these are forces and just need to simply be converted to torques. And so the formulas that we're going to use to do torque due to friction torque due to gravity and torque due to work. And remember, I'm putting plus and minus because really we're looking for worst case, because that's what the motor has to do. And if the motor can do the worst case, then it can do everything else. And so when you're designing, you're really trying to figure out, how do I minimize what the worst case is? So we're done with that one. Torque due to friction. If we look back on that diagram, hopefully you can see it. I've got torque due to friction on that robotic arm. There's one key component, torque, that includes torque due to friction. It's not just friction. There's two parts to this. One is a torque due to preload plus, and I'll just put something like mu times F and times R, right? And we don't really need that. We don't really have a denominator. Well, yes, we do. Well, I'll get back to that in a minute. So if you look at that arm that you had a robotic arm and it was moving around in the air. At first glance, there's no friction. What's a sliding? There isn't anything sliding. I mean, I guess if it was sliding something around, but that's not what we had. We were just carrying a mass around in a rotary motion. And there's really not any friction. So it'd be very easy to just go back and say, oh, torque due to friction is 0. And you might miss the biggest term that there is in the whole motor sizing, and that is preload. Everything has, as you put something together, I could also call this the torque due to poor tolerancing, too tight of tolerances. So the places in that arm that you would have preload are every single bearing. It's going to have a certain amount of preload. And the way to think about preload is if you went up to the very end of that robotic arm and you pushed on it with your finger, or anywhere along it, it would have a non-zero amount before it backdrove. It wouldn't just spin super freely. I mean, the only place we have super free loads is when you have on an air bearing or in the physics class when you get to ignore it. But if you have bearings, you have preload. The tighter you preload, the more accurate your machine's going to be. If you loosen the preload, you help yourself with the frictional torque, but now you start to introduce slop in there. One of the ways that bearings get preloaded most often is by oversizing the little ball bearing that they put in there. And most of the time you can buy the bearing at a certain preload and they will tell you what that preload torque is. It's non-zero and you don't think of it as a big term, but it's there. And a lot of times if it's directly connected to the motor, that's a significant amount of torque spike that the motor has to create in addition to doing everything else. Easy to forget. The gearing, if you put two gears together and they were meshing, at some point you've got to decide as you're holding the two axes, if we get, I'll just draw this a little bit better. So at some point when we have these two gears and you're trying to mesh them together, you've got to put them on an axis, and you probably need to figure out what bearings are you going to use. Are you going to use a fixed arrangement like a thrust bearing on one end and have it free? Or are you going to use simple? You've got to do something, but you have to then really be careful. I hate doing do-it-yourself gears because it's so hard to get this right. First of all, you end up buying gears from cheap sources usually because they're on their senior project and they're not perfectly round. And so you get spots that have more friction or drag, and you get spots that have less. Then the next problem you have is mounting them in the center. you have run out and concentricity. So you've got two problems. One is it's not perfectly round, and the other problem is you didn't put the hole in the center, which essentially now makes it not perfectly round. Then finally, you've got to really pay attention to how can you hold this distance right here so that you mesh the gearing within thousands of inches, or sometimes less than that, so that because in motion control, we don't want to get the slop in the gears. So you're tightening them up to a certain extent, but as you tighten them up too much, now you're getting into a point where they can start to bind if they're not perfect, but now you're getting into the additional preload of gearing. Back it off a little bit, have lots of slop, no preload. But now you lost motion. Every time you switch direction, part of the motor went to do nothing, and then it hit the edge. So most of the time when we're dealing with motion control, you aren't just going one direction, you are going back and forth, moving some sort of mechanism back and forth. So this preload, sometimes you can look it up. Sometimes you have no idea what it is because it's still being designed, it's still on paper. And so I'll help you guess when you get to that, or estimate. I'm sorry, we don't guess, right? Engineers don't guess, we estimate. And then once you get over to the actual friction part of the formula, then you have a denominator underneath this, and the denominator still has an inefficiency. Same kind of thing. You got a same procedure. You kind of play the Ninja Warrior and walk backwards and find all the inefficiencies, because every time there's an inefficiency, it requires a little bit more torque to overcome that preload, and that's what takes care of it. And then you have a gearing, and this is now, before in inertia, this was a squared term because it was working on the inertia. Now it's just a regular gear ratio. And so your speed and torque trade off according to your gear ratio, right? So that would be a linear version, and there's no this is a rotary version. There's no linear translation required on this stuff. Torque due to gravity. Anything special there? Not really. In this case, you don't have mu and F, you have mg. Then you've got to that's basically your force times the radius that the force is acting on. Maybe it's the radius of gear 2, and then efficiency and that. So the only thing that changes there is, again, we're dealing with where are the forces, and the force is a force due to gravity, easy to calculate. Okay, torque due to work. I don't know. It's a force. It's some force. Force due to work times the radius it's acting at divided by the same two things. Put them in the denominator. Okay. So these are things that when you go through it, you get to go revisit your physics and you think through it and you write it out and you get confused. And then the more you stare at it, the clearer it becomes. And so when you bring to me a motor sizing and you want me to check it, what I'm going to do, I don't even care to see your calculations unless you can't find an error, and then I'll help you there. All I'm going to really do is look at your sketch, a labeled sketch, bring me that labeled sketch, and then I'm going to look to see if the formulas that you wrote match the sketch. And if the formulas are right, you're good. Then you can go, once you've done them in this form where you can see units cancel, then you can go ahead and put it in to whatever solver you like and let it iterate. The trouble I would say to add on to, maybe the fifth error that you make is you have to do this motor sizing the first time with regular algebraic formulas. You've got to be able to watch the units cancel. You can't, if you've ever gone and looked at a spreadsheet where there's formulas in the spreadsheet, it's pretty much impossible to, because first of all, it's not written in standard algebraic forms. It's got parentheses everywhere. It's really easy to make a mistake in building those formulas. And there's probably an app that you can put in algebraic and it'll create the Excel formula. You could probably, maybe you've used some of that. But in general, this writing it out is kind of still how it's done until, the first pass, until you begin to iterate. Then, and your formulas are right, then you can go ahead and put them in, see if the numbers match your original algebraic form. Once the numbers match, then your formula is right. Then you can switch to the electronic version and do it over and over. And that's important because as you're designing, you're trying to design things for low inertia, see where the forces act. You're going to come up with different designs, and you're going to need to iterate. And I think if you look at the very last line of the 7 steps of motor sizing, what does it say? It says, it may be necessary to adjust mechanics, add gear reduction, and start over. Remember, iteration is critical. You don't get it right the first time that often. Okay. I think that's it for rotary loads. One thing I'd like to mention about this system, let me see. Let's go through the 7 steps of sizing for a minute. I'm kind of following along in the 7 steps. So we did step 2, we did the motion profile. Then we did step 3, where we actually calculated the actual inertia of the bodies. That's the MR squareds and the hollow cylinder kind of thing. So we actually know what number to put in there.
Hey, Dr. Epinish.
Yeah.
The question, I was wondering, say we're pretty lazy and we don't want to have to try to calculate the inertia values for everything. Are you able to do that on a program like SolidWorks if you have like a complicated system going on?
Yeah. Complicated, I don't know. That's usually the problem with motor sizing programs, is that if you use this little Ninja Warrior thing and just write down the formula as it comes to you, you end up these big formulas, but they're actually really easy to create. And I've yet to see a thing in SolidWorks that, well, they never calculate torque, but I have seen on individual pieces that the inertia is pretty accurate. And so I think take a shot at it and see if it'll tell you the inertia about this point with all these other things, and these, it is a number. But in general, you can get that inertia value from SolidWorks, yeah.
And you think that would be a bit more accurate to the actual inertia value as opposed to trying to calculate it with simplification?
You don't care. You don't care if it's accurate right now. You don't need to carry 5 digits after the decimal point right now. You're estimating. What's the machine look like? Well, is it going to change? Absolutely, right? So really, all you're trying to do is find out at first: is it a 3 horsepower motor? Is it a 1/4 horsepower? What power range are you in? Oh, okay. Now you can maybe do some energy calculations if you got to figure out what battery you're doing, so you know the weight of the batteries. There's a lot of things that hinge on what you're doing here, but you're not carrying digits right now. So it doesn't matter what SolidWorks says in terms of, it's not 4.382, it's 4 or maybe 4.3. It's as good as you need right now. Later on, and especially if you're going to build 100 of these, then you're going to get more accurate. But most of the time on the first one, keep in mind the very last thing you're doing, you're going to calculate a number. Then what are you going to do when you go find a real motor? You're going to add in your safety factor, right? You're going to add in a margin. You might double it right there. You're not going to just go find a motor that just does this. You're going to go add in some sort of torque margin or factor of safety. And so since you know you're going to, and who picks the factor of safety? You guys do, right? And so if you pick a factor of safety of 2.2 instead of 2, or 1.8 instead of 2, or 4 instead of 3, those are huge changes. So you can see right away, it's like you don't need the accuracy of SolidWorks. You just need to get an estimation. So you don't want to make this a huge effort the first time. You just want to get it done, see what you kind of think you might have, put it away, then continue with your design, right? Or you might say, hey, group member B, you designed a system, but look at this inertia. Look at the value that I got for this inertia. Is there any way we can do this? Because you designed in this part, we want to move this thing way over here. And really, you designed a thing that all it does is move this hunk of metal. So maybe we ought to make it aluminum. Maybe we ought to hollow it out, do a little machining on that to reduce that inertia. You're in an iteration anyway. Make sense?
Yeah, thank you.
Okay. So then you're going to determine the worst case of all of these. You're going to determine the worst case of that formula. It may be during the acceleration part. It may be during a deceleration. It may be when it's not moving, and sometimes all these things don't happen during a move. There might be work that's being done afterward that it needs to hold against. And so you have to look at each time period during your whole motion profile and decide what is the peak torque for that part of the profile. So for instance, if you had a motion profile, if you had a motion profile that had some acceleration, and this is speed versus time, and then you cruised along at some velocity, and then you might have a different slope for your deceleration rate, perhaps. Then you had a period of time where it did nothing. Then you had some really fast move back, and then it sat there, and then you start the cycle again. So what I just drew is 1, 2, 3, 4, 5, 6, 7 before it starts out again. So there's 7 individual places that you're going to have friction and gravity and work changing. The one thing that doesn't change is if you are accelerating, you have to accelerate inertia. So it needs torque. One other thing to keep in mind, this motion control, we're doing this kind of as an absolute value when we're saying worst case and with the plus and minuses. And the reason we get to do that is because the motor doesn't, once you move to a stepper or a servo, it doesn't care which direction it's going. If it's getting positive voltage, it goes that way. If it gets negative voltage, it goes the other way. And an H bridge is what allows you to switch that voltage across the winding and get it to reverse direction. So everything we're doing ends up kind of being an absolute value on the torque, and we don't really care about which direction it's going, because the motor doesn't care which direction it's going. As long as current is proportional to torque, you're good to go. One of the things that you'll see is after you've figured out which one of these 7 is the worst case, I'm going to ask you to go back and say power is equal to what? And it's torque times speed. But one of the things that I would like to know is the power range. And the only reason you really calculate this power term is it's part curiosity. Is this a big motor or a little motor? But it also lets you find out if you had the sense that you're putting a motor in a scooter and you have this sense that the motor is, it's only this big, it's not going to be maybe more than a half a horsepower needed to move. You don't really know, but if your numbers come out and the power comes and says you need an 18 horsepower motor, like, oh, this is I guess not error checking, but reality check. Because if the power is, or you might find out that if you come out and you see the power is equal to 0.6 watts. Huh? Really? We only need 0.6 watts to move a person along a street in a scooter? Okay, that's not right. And so you get a reality check by checking the power, but you're not really going to use it, because in order to actually select a motor, what you're going to go do is you're going to go to find a torque and a speed, and you're going to look for some curve, and then you're going to say, oh, well, the torque that I need is at this speed right here. I need that amount of torque, therefore that's the operational point, right? And so you say, oh, well, that's not bad because I have a good safety factor right there. I have a little bit of safety factor in speed, which is kind of important in servos. And so anytime you want, you can calculate what is the power at that point. But in reality, when you go to choose a motor, it doesn't, unless it's motor control, but in motion control, you need to create enough torque to do the job. And so this whole procedure is mostly designed to have speed torque curves available from a manufacturer that you can compare your numbers to. There's different ways to do sizing where you get and we'll get to it in Mecha 486, but it's way more advanced where we're dealing with torque constants and current and stuff that you really don't need to do. You're probably going to go find a motor that has a published curve, speed torque curve, that you can compare your numbers to. If you get into those situations this semester and you need to do that, I'd be glad to help you. You just send me an email and we'll schedule a time and we'll go through your sketch, go through your vectors, and see if there's little things we can do to make it better. So once you've found, keep in mind though, there's one thing that this formula, I'm going to go backwards for a minute. Back to the very beginning. One thing that when we got to this point here, you notice that we wrote the formula and we made sure that we included the motor. But this is kind of a chicken and egg thing, because we don't know what motor. We don't know how much torque we need. So how are you supposed to put in the inertia of a motor that you don't know yet? You haven't even selected it yet. So what you do on the first pass through this is you do it first just the load without any motor, and you get an idea what does the load take to move. And then when you go to select a motor, the very first thing that you're going to look up when you go to actually select this, if you selected that particular motor that had the speed torque curve, the first thing you're going to go look up is inertia of the motor. Oh, I know, I just screwed you up. You know what? You guys want to go look up the inertia I of the motor. In mechatronics, we have too many I's. And so we kind of had to decide, is I going to be used for current or is I going to be used for inertia? And since inertia has another term that's not quite right, the area moment inertia, we tend to write the formulas. We don't use I for inertia. We'll use J for inertia, and we'll put an asterisk that says, yeah, we know we're using it wrong, but it's inertia. It's mass moment of inertia, not the area moment of inertia, okay? So, but I'm going to use J anyway, because later on, we need, mechatronics is got onyx in it. So, but one of the things when you're selecting this, safety factor up to the speed torque curve, on your first pass through, you only have the load. So you probably need to bump up and make sure that you have enough safety factor that when you add in the motor inertia, that you have room. This isn't very hard to estimate because once you know the inertia of the load, all the different parts of it, when you go to look up the inertia of the motor, let's say the inertia of the load all adds up to 56. Random number, 56, I don't care about units, but that's the number, 56. So we have 56 for the load. And if you go look up a motor, this particular motor, and you say, oh, that motor has an inertia. The inertia of that motor is J, the motor is 0.8. You know right away, most of the power, most of the torque is going to move the load. Very little is getting added onto the motor. This isn't the way it usually works, though. The way it usually works is that the J of the motor is more likely to be like 12. And so I was like, oh. And so this is kind of one of those things you can look ahead. It's like, well, if you're going to add 12 units of inertia to a 56 and end up with a total of 68, all right, now you know the motor's going to have some acceleration, some torque needed to accelerate it, and you can adjust your safety factor right then. So you kind of see the nature of the chicken and egg thing.